Okay, thank you. Right, I will talk about what can be done with shear code, but I will start a bit far. I will give some background, maybe, what questions we want to answer. Where do we look? And here is a bit outline of my talk about ultra-fast non-equilibrium phenomena. Emphasis is in my talk on atomic molecular and condensed matter physics as a remote goal. So then I will talk about theoretical formalism, and I will give, if time permits, 3 applications of linear scaling algorithms that were done basically with cheat code. And then I will talk about the prospects. So about ultra-fast non-equilibrium phenomena, a laser is a crucial ingredient to this. And you would find funny that the very first photo emission experiment was done many, many years ago by Hertz, and that's the experimental setup for the photo emission. So basically, you look at the spark between 2 spheres if you have UV light coming from the spark from other 2 spheres. Very interesting effect, because UV light stimulates the spark. Yes, so this is exactly the photo emission effect. Okay, but now we have, I think I update this number often. Time ticks. There are many years of history of photo emission, and now we have this powerful machines, free electron lasers, different experimental apparatuses. And of course, we can now expect from experiment a much deeper analysis of what's going on. I am very much impressed by one experiment, which is called attosecond streaking. So attosecond, we have heard this word today already in discussion of the different regimes where the electron dynamics takes place. And attosecond, that's where everything starts. Yes, attoseconds and femtoseconds and okay, very good. So attosecond, femtosecond, picosecond, that's time regimes that are interesting for us, right? And in this particular experiment, they have 2 basically laser pulses, XUV and near infrared. They are locked, they are phase locked, and they can measure processes on the attosecond time scale. For instance, the emergence of screening or the photo emission from different atomic shells. Okay. So let me maybe mention why non-equilibrium phenomena are of interest. Of course, on one side we have these experiments that provide us with material to understand. Attosecond streaking, that's what I was mentioning. Terahertz spectroscopy, time resolved ARPAs. We have seen this the discussion about these experiments today and before. And we want to answer some fundamental questions. For instance, how quasi-particle excitations are formed in many body systems, how collective orders are formed, and what is collective order? Could be, for instance, plasmons, or could be some non-trivial phase, and so on. And generally, one desires to go a bit further. One wants to build the matter up to your preference. Yeah, you want to construct the matter, but by putting it in the interaction with laser. So one can think about Fouquet engineering of, for instance, topological insulator or light-induced phenomena or non-equilibrium excitonic insulators. So these are phenomena that for sure will be addressed in the next decade. But let me start with something very, very basic. Because we talk about, let's say, photoemission, and it's unavoidable that we talk about spectral function. So what is photoemission? You all know very well. You have laser photon coming to a system. It ejects an electron, and notice this fuzzy stuff left behind. This is not real whole. The system is interacting, and so it means that left behind is some kind of hole dressed by other quasi-particles. And this is a signature of many-body effects, and we can see it in basically in the spectral function. So if the system would be non-interacting, we would see electron in the detector at one particular energy. But because we have interactions, so the peak will be shifted, and this is called the correlational shift. And what is responsible for this is a real part of electron self-energy. But in addition, you will see broadening, and you will see the satellites here. And you would be very much surprised that we not only want to look at the spectral information, which would be just normal ARPAs, for instance, but one might think, oh, maybe electron comes with this energy a little bit later than with this energy. And indeed, the time difference is in the range of attoseconds, and such experiments have been performed. I will discuss the experiments, but let me just say that if we this satellite here is due to the quasi-particles of bosonic nature in the system. Can be, for instance, plasmons, can be phonons, can be other things. And if you want to learn as a student about physics of electrons and bosons, a good place to start for you would be to look at the Langres model. And the Langres model is a very basic model which describes a single particle, let's say an electron or a hole coupled to bosonic excitations. And you see the typical spectral signature of this effect is that you have a quasi-particle peak and a sequence of satellites. Okay, so coming back to the experiment that I want to mention as maybe appetizer. So there was an experiment where on tungsten, performed on tungsten, they noticed that electron coming from the conduction band and coming from 2p band, so from core state, they come with a delay. And then they repeat experiment in a little bit different setup, and they also look at electrons coming from the quasi-particle peak and from the satellite, and they also found a small delay. Yeah, and this satellite is a signature of bosonic particles in the system, for instance, plasmons, and that is worth of describing this little time shifts. So now let's come to theoretical formalism. How do we treat this? So there are a lot of challenges in describing such systems. And maybe we want to always perceive our theory from positive sides, but let me talk about difficulties. So the difficulties are the following. Very often we have different energy scales. So phonon energy and electron bandwidths are very different. Yes? So if you look at spins, so the spin exchange interaction versus on-site Hund interaction are also very different. And then non-local Hubbard correlation versus a local Hubbard correlation versus non-local screen. They are very much differently localized in space. So this all complicates. Yes, whenever we have two scales, we need to study the system on the smallest possible scale, but at the same time, long enough to capture the bigger scale. And this is really a problem, and it calls for very efficient methods to deal with this. Here we need a method that is efficient in time. Yes, of course, I have to mention different bosonic particles in the system that can be present. Well, here is a picture of nickel oxide, which would be a typical system which is difficult to describe because you have spin exchange interaction, you have strongly correlated physics, and so on. So keep this in mind as maybe a possibility where the theory needs to be developed. So as I mentioned, we need a theory with quantized bosonic fields, and we need to describe spectroscopic experiments like photoemission. So it means processes with variable particle numbers, for instance, in molecular systems as shown here. Okay, so these are the difficulties and challenges. How do we deal with many-body aspects? In particular, for electron-phonon systems, the arsenal of methods is a bit smaller or a bit different than for pure electronic systems. So it has to do with the fact that that you do not have Pauli exclusion principle for phonons, and you at each side you can have many phonons. So one possibility to do this is a so-called matrix product states, which is basically a wave function approach. Another is time-dependent density functional approach, and there are some strong developments for let's say electron-photon systems. And then I have to mention density matrix theory, Boltzmann equation, which has a long history, and non-equilibrium Green's function approach. We should think that there are many species of doing, there are many possibilities of doing NEGF in real life, and one can think, for instance, combining NEGF with dynamic mean field theory. Okay. So what is NEGF? You have seen, I am sure, on the first day, and on the first 2 days, you have seen what is NEGF, but I think it doesn't harm to a little bit what is this. So we start with Kadanoff-Baym equation. What do we see here? We see our unknown, which is G, Green's function. Very important that you pay attention. There are two-time arguments, and this is where complexity is. This two-time arguments, as times are on Keldysh contour. So they create a problem for theory because we want to propagate everything in time, but we have two-time object, and it results at best in a method that scales cubically with number of time steps. I have to say so that the Green's function formalism is very good because it allows one to compute all possible transport properties, time result photoemission spectroscopies, and it's often enough to look at the time diagonal Green's function, which is the density matrix. So, and all correlation effects are hidden in self-energy. So, the full solution of this equation is very hard. To my best knowledge, the first solution for inhomogeneous system like molecules were obtained just in 2009. In 2016, we managed to solve this equation together with bosons. And I tell you, even in the simplest case, the calculations run for hours. So very inefficient because we have to propagate in the time, in the 2 times plane, yes? So we propagate in the 2 times plane. But there are benefits of doing this, because if you look, for instance, at the Lesser-Green's function, you see that it has 2 aspects. If you look at the time difference, you will see oscillatory pattern, and it encodes the spectral information. If you do the transformation to the frequency space, you will get spectrum. And if you look at the time sum argument, you will get populations. So this is the object that has population dynamics and spectral properties. Okay, and that's why it's so beneficial. But if one is interested only in populations, for instance, one can simplify the theory. So I just show you briefly that relating to this attosecond experiments, we could perform calculation for electrons coupled to plasmon as a bosonic particle, and we see the shift, for instance, of satellite from lower energy to higher energy. We see some correlational effect that cause the oscillation of the bosonic occupation number, but at the same time, these calculations scale very badly with time. We also could predict, for instance, a tiny shift in the photoemission in time between the peak at the quasi-particle energy and peak at the plasmonic satellite. Okay, so this was an appetizer. Let me show now the applications. So the prerequisite is a generalized Kadanoff-Baym ansatz. As you look at the sketch, you will see that it's tempting actually to decompose it in some kind of product, yeah, to separate spectral and population dynamics. And this can be done in this form, where we write a general lesser or greater Green's function in terms of retarded or advanced Green's function, which carry only spectral information, and populations. Rho are populations. This was proposed a long time ago. Recently, it was generalized to bosonic particles, and the form of the ansatz is very similar. But it's important to emphasize this is not a diagrammatic approximation. It's an approximation of a different kind. Okay? So, but with the use of these approximations, we can make a drastic simplifications of the equations, and these equations are now implemented in GS2 code. So the simplification is that we go from times objects to one-time object. We look basically only on the densities, which are the function of single time, and these objects, they are parameterized by using the mean field approximation for these objects. Here, and here, and here, and here. So reduction to single time object. What does it mean in terms of equations? Of course, you don't need to memorize these equations or be able to understand how to derive them right now. Yeah, the message that I want to give you by showing these equations is their structure. So let's look at the structure of these equations. We have equal time objects, which is electron density or the bosonic density. Think phonon density matrix. So these are density matrices. They fulfill a normal equation of motion with a commutator here and some effective one-body Hamiltonians. But the complexity of the whole many-body problem is hidden in the collision integrals. In these collision integrals. Collision integrals instead are, so diagrammatically, they can be expressed in this way for electrons, and you have bosonic contributions. So collision integral is nothing else as a G times sigma. And G times sigma is in general 2 times quantity, 2-body object. But this object in the GKBA approximation is can be recasted in terms of equal time two-body, so higher order correlator for bosons and a higher order correlator for electrons. So this is really, really important. We have a system of coupled equations which can be used, which can be propagated with standard solver for ordinary differential equations. So, and it can be used to compute different observables. Observables that depends, for instance, on the electron density, on the bosonic density matrix, or on these two body correlators shown here. Okay, so the structure, I want to emphasize again, we pay a price. The price that we pay is generalized Kadanoff-Baym ansatz for single particle lesser objects. But the benefit that we got is reduction from cubic to linear scaling. Linear time scaling is very important to mention. I am talking about linear time scaling. Nonetheless, the computational scaling with the system size, it's a completely different issue, and it can also be demanding. Okay. So I skip a bit of history. This is maybe not so relevant for today's talk, and I go to the application of linear scaling algorithms. Okay, application number one is a narrow bandgap semiconductor excited by laser. Complication in this model is that we have acoustic phonon. So here is our setup. We have two bands. Laser comes, excites an electron, and electron, we want to describe the relaxation of electrons towards the band minimum by interaction with phonons. And here you see two self-energies for electrons and for phonons that we take into account. And this is our coupling between electrons and phonons. Okay. So we were able to propagate the system for a rather long time to achieve the thermalization. And let me explain very little what we get. So you see these two peaks, they are caused by coherent laser excitation. Then no phonons initially. Immediately, electrons interact with phonons. Population of phonons rises at the bottom of the band. But also you see appearance of this satellites approximately at the momentum of these electrons. At the end, all electrons gather at the bottom of the conduction band, and we have localization of bosons at the phonons at the bottom of the band, but there are also these side bands. So here are some information about this. So we have initially hot electron distribution, we have thermalization and reabsorption, and the final, we can use the final equilibrium temperature for electrons and phonons, much less, of course, than initial one. And we see the persistence of this side bands here. So it's important to say that the difficulty in the simulation is because we have two time scales. Remember my second slide where I was complaining about multi-scale. So here we have multi-scale. We could achieve a sufficient long propagation in order to capture effect associated with acoustic phonon frequency and coupling to the phonon square divided by acoustic phonon frequency. These are two distinct energy scales. And here I would like to emphasize a bit the capability of the code. We could do the propagation with 1,500 K points for 15,000 time step on a single CPU in very reasonable time. I don't remember what was that, but definitely not days. It's not days. Okay. Next one. Two-side Holstein model. The system is super simple and was used in many works to study electron-phonon interaction. So what we have? We have a Hubbard model with just two sides, and electrons are coupled to the phononic displacement. How we initiate the dynamics? The dynamics is initiated by suddenly turning on the coupling. And what happened immediately is that electronic natural occupations start to oscillate, and bosons start to appear in the system. Again, we have two distinct time scales here. One is connected to the hopping constant, another is connected to the splitting between two lowest energy levels, which is in turn depends on omega and on the coupling strength. So this effect is not possible to describe on the mean field level. This effect is very hard to describe by freezing, for instance, the bosonic self-energy, as done in many other works. Yes. So in order to get a good agreement with exact results, we are forced to include these two diagrams, which, by the way, also ensure the conserving properties of theory. And here, look at these numbers. Full solution of the Kadanoff-Baym equation took 1 hour, and the solution in the GKBA form just took 1 second. This is the speed up that we are able to achieve. And yes, so we will, this is one of the test examples that we will also study today in the tutorial. Let me talk now about a completely different system, much larger again. We go to larger systems. We have a Holstein-Hubbard model. And this Holstein-Hubbard model is important because it's used as a model for photovoltaics. What is photovoltaics? So these are materials that absorb light and produce electricity. And what is the process there? The process is that a photon comes and creates, for instance, in organic chain, creates electron-hole pair. So in the conduction band, suddenly appears an electron or a pair of them, and they propagate along the chain. So this is a prototype of photovoltaic material, and the model is simple. We have a hopping term. We have interaction, for instance, between spin up and spin down electrons, and we have coupling to the phonons. One can differently excite the system by either vertical transition or from minimum to minimum. But the physics is basically very simple. If we increase the coupling to the phonons, electron doesn't want to spread. So if you drop an electron in the middle of a chain, you know from quantum mechanics, electrons spread. Yes, this is the spreading of Gaussian wave packet is a standard topic in quantum mechanics, right? But interestingly enough, if this electron couples to phonons, it doesn't want to spread. And it's very easy to see if you compare the weakly interacting and strongly interacting case. In weakly interacting case, it still spreads. In strongly interacting case, the electron density stays in the center. So we have the effect of self-trapping of polarons, and one describes this often in terms of renormalized hopping constant. You see the hopping constant is renormalized by this factor here. Okay, and we want to describe it in real time. We want to drop really the electron, 2 electrons in the middle of the chain, see how this wave packet spreads. We do this with our GS2 program. So self-trapping of polarons, and there is this very nice picture that we have basically. So in talking about quasi-particles, we start by analyzing what is a bare particle, right? And what is a quasi-particle? Quasi-particle is a bare particle dressed or surrounded by other particles, which would be phonons in this case. Yeah, you see basically a cloud propagating. You can imagine that to propagate a cloud is harder than to propagate a single horse. Yes, so then why the model is interesting to study and why it is difficult at the same time, again, because we have a number of energy scales, we have electron bandwidths, we have doublon binding energy, and a binding energy of a polaron. These are different energy and time scales. So what we do here, we do T-matrix theory in particle-particle channel, which provides results very close to results in absence of phonons. So you see dashed line for the distribution of electrons. Dashed line means approximation, and full line means exact theory. So you see quite good description. And we can now proceed to show the full power of non-equilibrium Green's function, to study really all possible approximations and the effect of them. So let me just show you few. Here, you drop 2 electrons in the middle, but they don't interact with phonons, they don't interact with electrons. And you see a perfect spreading. It turns out that when we treat phonons on the mean field level, which is called Ehrenfest approximation, nothing happened much. Then we can add interaction with phonons in GD approximation. Remember the self-energy diagram. You see some localization happen here. Then we add second bond approximation, next level of approximation for the interaction between electrons. This approximation is not accurate enough. It doesn't predict appearance of any doublons in the system. So black line is a doublon excitation. What is doublon? It's 2 electrons on the same side, right? The correlated part of this probability. Okay, and then we have most advanced method. This is T-matrix plus a GD approximation. You see that electrons and doublons spread slower, and each one of them with own speed. Yeah, here you see some more investigation. I will not go into the details, but the point is that we can study such effects as different mechanism affecting spreading of the doublons. So this would be phonon renormalization of hopping or reduction of the effective electron-electron interaction by mediated by phonons. Okay. How many minutes I have? No. Yes. Yes.
On the top panel, what do you get, say, localization of doublons on the surface of your chain? At the very top, like this one here. Well, is there any simple intuitive picture why they localize on the borders, or and not say at the center?
Good question. I don't have any intuitive picture for this, No, I cannot say.
Because if I would make the system larger and larger,
Yes.
would they just also see, they would mean there is no double at all in the middle, or?
Yeah, almost there will be no.
Okay.
So there is a time limit on how long you can propagate, but that seems to be the tendency. I cannot say why.
Okay.
Yeah, so there are many things to look at here. Yes. Okay. Well, I think according to my time, I still have 10 minutes. No. It was delayed. Okay, good. Let me show a few more results, and I will. It seems that I have to skip some. I don't want to delay your lunch. Here we could study with our approach. Different contributions to the total energy. We can study, for instance, how the equilibration is done. So the exchange between mean field electron and phonon energy, but we also have different correlation energies and effect of relaxation of doublons and generation of due to the generation of correlations in the phonon channel. So this all is possible to study with our code. And let me just show very briefly what are the advanced methods, what we can do. One of such things is to study a renormalization of electron phonon interaction and electron-electron interaction. And the normalization is done by opposite particles. So it means electron-electron interaction is renormalized by the screening by phonons and vice versa. So these are the sets of diagrams that we can include in our theory. In the previous case, we study only this Baym functional, which give rise to the simplest electron and boson self-energy. And here is the full sequence of diagrams. And with this, we could study, for instance, effect of Gly-molecule in optical cavity. So it means we excite the Gly-molecule by a laser. The molecule interacts with a mirror. And what we see, let me just show the final result of this. So basically, this is exact calculations. This is a second Born plus GD approximation. You see the energies are completely wrong. We do not see the splitting in the spectrum. If we include electron-electron correlations, we see the improvement in the energy of the spectrum, but we still do not have the branch associated with the cavity mode. And only when we get to the most complicated approximations that we can deal with, we get the full picture, albeit a bit shifted. Okay. So prospects. There are many interesting phenomena that one can study. One can classify them by the typical frequency or energy of the excitations, and this can go, for instance, from spin excitations to nonlinear phononics, excitonic insulators, until the Auger effect, which is in the XUV regime. And for this, we are developing our Cheers code. Currently, it has two parts that you will be able to look at today for molecules and for lattice systems. And by this, I would like to conclude. So I was talking about time result spectroscopies and quantum materials on demand. Full KBE is highly accurate, but feasible only for small systems. And GKBA ODE scheme is implemented in Cheers 2 code. We can control the level of accuracy by choosing the self-energy. And we have linear scaling with propagation time. So our aim is multi-scale systems, transport, photoemission. Maybe at some point spectral information, but it's a bit more difficult to discuss. And with this, I would like to thank you for your attention.
So thank you very much, Jaroslav. And so we have time for a few questions. I would like to start from the students, if possible. If there is any question.
Yes, everyone is hungry.
But okay, otherwise I will start with a question myself. So you have shown in the last model the comparison versus the second-born GW and then this GW tilde.
Yeah.
Can you comment what is this GW tilde?
Yes, so when we do, yes, I was a bit too fast in this. Let me go back a bit. Our standard approximation is very simple, how we treat electron phonons. So let me go back here and I show the diagram. So the phonons affect electrons in the following way. Electron flies and then emit phonons and then recombine. So this is how you can explain very in layman terms what happened to electron. And phonon flies, emit two electrons, and they recombine. Yeah. So this is a physical picture. Okay, but there is a lot of things missing. Let's go now to more complicated diagrams. What is missing here? Missing is screening. So imagine you want to look at the interaction between electrons, effective interaction. So effective interaction can be denoted by this funny curly line, can consist of interaction, bare interaction between electrons, plus interaction mediated by phonons. And this kind of effective interaction have to be inserted everywhere in each possible diagram. So that's why the usual screening is modified, because in the screening we include effects of two kinds. Each interaction line is in fact line that carries either Coulomb or carries a phonon. So because of this, we have a much more complicated screen, and so that's what. So we have dynamical screening to both electron-electron and electron-phonon interaction. So this is a distinct feature. Yes, if you look at your familiar GW theory, GW theory doesn't have this inside, and so you see that this comes in every possible order, and this seems to be important to reproduce this spectrum.
So the splitting of the spectral line you had is due to the coupling of the phonon entering dynamically.
Yes. So this is okay. Yes, that was unexpected for us, that we could see this physics. We actually were not planning to discover this approximation in some way. It came out of the calculation. We were pleasantly surprised.
Okay, so one more question.
Can I ask a technical question about your impressive speed up from 1 hour to 1 second? How it actually scales with the size of the system?
Oh, excellent question. Excellent question. How it scales with the size of the system. Okay, in the worst case scenario, when we have, let's say, molecular systems, it scales like N6. And there is a super simple reason to understand this, because we propagate two particles quantity. Let me go very quickly back. Sorry for delaying. I will try to be super fast. You just need to, yes, so have a look here. Not only that we propagate density, we propagate two particle quantity. It depends on two indices, so it's matrix n² by n². Yes, where n is the number of basis functions. So if you propagate n square by n square object, at some point you have this horrible product involving the Coulomb interaction, and you get n squared to the cube, so 6 power scaling. Yes, but for lattice systems, very often we can take into account much simpler form of Coulomb interaction that is localized. It doesn't have 4 indices, but instead only 2 indices. In this case, we can reduce scaling to the 5th power. So basically, the scaling is n6, n5, and if we go to mean field, of course, it will be n4 with the system size. Yeah, 4th, 5th, 5th, and 6th power.
Just for comparison to this KBE equation, what is the scaling of KBE?
KBE would be the same scaling, but you multiply by cubic scaling with time. So
sorry, I didn't get this.
Yeah. So yes. So the spatial part scales in the same way, but the time part scales as t cube, while in our case scaling is linear. Yes. So
linear and cubic scaling, yes, right?
Yes. So let me write on the board. Of n6 t cube and GKBA plus ODE. You cannot. I will. I don't know. Yes. In other cases, this is n6. Let's say t first power. So you still have a scaling with the system size the same, but much faster with respect to the time.
Okay, so now I think it's really time to move for the lunch, and we resume the session in 1 hour, so 2:15. Thank you.